When analyzing all of the forces acting on one object, we use free body diagrams. A free body diagram shows all of the forces acting on one single isolated body, which makes it possible to discuss and determine the behavior of that body without referring to any of the objects exerting the forces. When drawing a free body diagram, we draw a point to represent the body, and sometimes we put a square around it. On your free body diagram, show each force of the object with an arrow. The direction of the arrow must be the same as the direction of the force. Whenever possible, the length of the arrow should be roughly proportional to the size of the force. Each force of the diagram must be labeled. For example, if it is raining, what forces are acting on the rain? Well, it is pulled down by gravitational force, and there is air resistance acting against it upwards. Newton's first law is the law of inertia. It states that objects at rest stay at rest, and objects in motion stay in motion unless acted upon by an outside force. So, why does a moving block come to a stop after nothing affects it? What you don't know is that there is a net force acting against the object, which makes it come to a stop.
Newton's second law is F equals ma. F equals ma, meaning force is equal to the mass of an object times its acceleration. Acceleration is created by unbalanced forces. An unbalanced force is when all the forces acting on an object don't cancel each other out. If the forces of an object are 5 newtons to the right, the acceleration will be 5 newtons to the right. Acceleration doesn't occur when the forces are balanced, which means all forces cancel the other forces out.
In this experiment, we use a 500-gram weight, and it uses gravity to pull the cart to the left, causing an acceleration. In this next experiment, we use a 200-gram weight instead, which applies less acceleration to the cart this time, as seen there. Newton's third law is every action force on one object has an equal and opposite reaction force on another object. If object X pushes on object Y with a force of 8 newtons to the right, object Y pushes back on object X with 8 newtons to the left. When object X is on a table, gravity pulls it down with some force, depending on its mass. For example here, we use 5 newtons. X pushes down on the table with 5 newtons due to gravity, and in order for there to be no acceleration, the table has to push 5 newtons up to balance all the forces and have the end result be no motion. On this table, there is a 1,000-gram weight. Gravity pulls this object down to the earth with a force of 10 newtons. That means that the weight is pushing down with 10 newtons on the table, and because there is no motion occurring, there has to be 10 newtons pushing up from the table to counteract the gravity force.
A very important force is gravity. Gravity is the force that pulls objects toward the center of the earth or towards the center of any other mass. When an object has more mass, then there is a stronger force of gravity. When there is a smaller distance, there is a greater force of gravity. The equation for finding the force of gravity between two objects is to multiply the acceleration of gravity, which is 9.8 meters per second squared, by the masses multiplied and divided by the distance squared. Since the distance is squared, it has a greater impact on gravity.
In this experiment, I drew out my Rubik's Cube from around 1 meter. On the surface of the Earth, all objects have an acceleration of 9.8 meters per second. Based on that, this cube should fall in exactly 0.4516 seconds. And this is around what it would look like in normal time.